The images you are seeing were captured by the Hubble Space Telescope, but this time they do not show an object quietly drifting through space. 3I Atlas is releasing a powerful jet aimed straight toward the Sun, pushing against forces that should be driving all material away and tearing it apart. When scientists stacked multiple frames together, something unexpected appeared. Not a normal comet tail, but a symmetrical, wheel-like structure, layered and repeating, stable to a degree that is hard to explain. Even more concerning, the object's motion no longer follows the familiar paths of natural celestial bodies. Instead, it shows signs of a directed force, as if its movement is being adjusted from within. Stay with us until the end of this video to uncover the unusual signs behind one of the most talked about astronomical objects of 2025. At first glance, 3I Atlas looks like a comet, but the direction of its jet breaks one of the most basic rules of comet behavior. In a normal comet, sunlight heats the surface, ice turns into gas, and that gas pulls dust outward, forming a tail that always points away from the Sun. This happens because solar radiation pressure and the solar wind act like a constant force, pushing everything outward without interruption. You can imagine it like dust thrown into a strong wind. No matter how hard you throw it forward, the wind still decides where it goes. For comets, the Sun is that wind source, and the result is usually predictable. This is why early reports of an anti-tail did not immediately cause alarm. In many comets, a tail that appears to point toward the Sun is only a geometric illusion. It happens when Earth crosses the comet's orbital plane, making old dust along the orbit line up with our viewpoint. From that angle, the dust seems to point sunward, even though it is not actively moving that way. However, 3I Atlas does not match this explanation. What observers are seeing is not a faint dust alignment, but a narrow and well-defined jet emerging close to the nucleus. This jet keeps its shape across multiple observations and stretches over a large distance. More importantly, it remains visible even as viewing angles change. That detail matters, because optical illusions disappear when perspective shifts, while physical structures remain. The real problem is the direction of the jet itself. It is pushing directly against the solar wind. The solar wind is not weak or temporary, but a continuous stream of charged particles moving at extreme speeds. For gas and dust to move toward the Sun, the source must produce enough energy to fight that flow over time. A simple release of gas caused by sunlight struggles to explain this behavior. If the outflow were random, it would quickly spread and bend away. Instead, the jet from 3I Atlas stays narrow, focused, and persistent. This suggests a source that is not only active, but stable. Another detail deepens the mystery. The jet does not appear briefly and fade away. It shows up again and again in stacked images taken hours and days apart. That consistency implies a fixed source region rather than chaotic surface activity. Most comets rotate unevenly, exposing different areas and causing jets to flicker. 3I Atlas shows signs of a preferred direction that remains locked in place. This raises difficult questions. A small object under intense solar heating should fracture, weaken, or change behavior rapidly. Yet 3I Atlas continues to hold its structure and repeat the same action. If this jet were just a rare natural event, signs of collapse should already be visible. Instead, the object remains intact and active. That forces scientists to consider uncomfortable possibilities. Is this an extreme case of comet physics we barely understand? Or is this jet driven by a mechanism that does not fit traditional models at all? And if a jet can push material toward the Sun, could it also be pushing the object itself in a controlled way? The strange jet was only the beginning, because the real shock appeared when scientists began stacking the images of 3I Atlas together. Stacked imagery is a simple idea, but it can reveal details the human eye cannot catch in a single frame. Instead of relying on one photo, astronomers combine many images taken over time to reduce noise and enhance faint structures. Random light fades away, while stable patterns become clearer with every added frame. This technique is commonly used to study distant galaxies, weak nebulae, and subtle comet features. When researchers applied it to 3I Atlas, they expected a cleaner view of the dust and gas. What they found was something far less ordinary. As the frames aligned and merged, a symmetrical structure began to take shape around the nucleus. It did not resemble a typical comet tail or a diffuse cloud. Instead, it formed a layered pattern, circular in outline, with repeating segments that looked organized rather than chaotic. Many observers described it as a wheel. More precisely, it looked like a wheel within a wheel, with inner and outer rings appearing at the same time. This is where the comparison to Ezekiel's wheel began to spread through the observing community. The name came from an ancient description, but the concern came from modern physics. Natural comet activity usually creates uneven shapes that change quickly as material disperses. Jets twist, spread, and fade as sunlight and solar wind pull them apart. The structure around 3I Atlas did the opposite. It held its shape across different stacked datasets. It appeared in images taken by professional observatories and independent amateur telescopes alike. That consistency made simple processing artifacts unlikely. If the pattern were caused by software or alignment errors, it would vary from one dataset to another. Instead, the same geometry kept returning. Even more surprising, traces of the structure appeared in some individual frames, not just in composites. That detail matters, because stacking can exaggerate illusions, but single images rarely support them. Seeing symmetry in raw data suggests a physical origin rather than a visual trick. The layered rings also showed clear boundaries. They were not smooth gradients of dust, but edges that hinted at repeated emission events. This implies that material was released in cycles, not as a single burst. Each layer looked like a record of a separate action, preserved in space. For a comet, that level of order is unusual. Most comets behave like open vents, leaking gas wherever sunlight finds weak spots. 3I Atlas appears to act more like a system with preferred directions and timing. That observation leads to a critical question. If this structure were random, why does it repeat so cleanly? And if it were natural, why does it show a balance that resists disruption? At this stage, scientists are careful with their words. They do not claim the structure is artificial, but they also cannot explain why it looks so organized. The data forces an uncomfortable pause. Because once patterns appear stable and repeatable, physics demands a cause, and that cause has yet to be identified. So the mystery deepens. If stacked images are revealing a persistent structure, what happens when we stop blending frames and look at the object piece by piece? What followed was even harder to dismiss, because when scientists examined individual images instead of stacked ones, traces of that same order were still there. What truly changed the tone of the investigation was the moment symmetry appeared in single images of 3I Atlas. Unlike stacked composites, individual frames are less forgiving and rarely hide mistakes or illusions. In several raw observations, faint but distinct arms could be seen extending outward from the central region. These arms were not random streaks or blurred dust trails. They appeared arranged in balanced patterns, usually 4, 5, or 6 at a time. Each arm curved gently, keeping a similar distance from the center. That balance is what caught the attention of astronomers. Comets are known for chaos rather than order. As sunlight heats their surface, gas escapes through cracks and weak spots without coordination. Jets form wherever pressure finds an exit, often changing direction as the nucleus rotates. This leads to shapes that twist, fade, and collapse within hours or days. The arms around 3I Atlas did not behave that way. They appeared steady across multiple observations taken at different times. Their spacing remained consistent. Their orientation did not drift wildly with rotation. This suggests the jets feeding them were not scattered randomly across the surface. Instead, they likely originated from fixed regions. Such behavior implies a stable rotational axis. If an object spins in a controlled way, material released from specific points can form repeating patterns. This is sometimes seen in well-studied comets, but only briefly and rarely with strong symmetry. In the case of 3I Atlas, the structure persisted longer than expected. The number of arms also matters. 4 to 6 evenly spaced jets require precise geometry. They suggest either evenly distributed vents or a deeper internal structure guiding the flow. Both possibilities raise questions. A small natural body should struggle to maintain that level of balance while shedding mass. As material escapes, the spin rate should change. That change should distort the pattern, yet the arms remained aligned. This hints at a self-stabilizing process. Some scientists suggest internal channels that regulate how gas escapes. Others point to a rigid body shape that limits deformation. Both explanations push against standard comet models. The idea of a stable core becomes unavoidable. If the nucleus were loose or fragile, symmetry would break quickly. Instead, 3I Atlas behaves like an object designed to keep its form. That does not mean it is artificial, but it does mean it does not fit comfortably into known categories. The arms also show signs of rhythmic activity. Brightness along each jet fluctuates in a way that suggests pulses rather than constant flow. This could indicate periodic pressure release inside the object. In natural terms, that might come from layered ice or trapped gases. However, those systems usually collapse after repeated cycles. Here, the structure holds. This combination of symmetry, persistence, and rhythm changes the conversation. The mystery is no longer about one strange image. It is about an object that behaves consistently over time. At this point, scientists are no longer asking whether the structure is real. They are asking what kind of physics could support it, because order on this scale demands energy, balance, and control. And understanding that foundation requires looking deeper at what 3I Atlas is made of and how it sustains such activity. One of the most difficult contradictions surrounding 3I Atlas is the growing gap between how small the object appears to be and how intensely active it continues to behave. Early brightness measurements led many researchers to believe they were observing a large interstellar body, possibly several kilometers wide, because only an object of that scale should be able to reflect so much light at such distances. As tracking data improved and models were refined, that assumption collapsed, revealing an estimated nucleus closer to 1 kilometer in diameter, a size that immediately changed how scientists interpreted everything they were seeing. In simple terms, an object this small should not be able to sustain such dramatic activity for long. Surface area matters in space because it determines how much sunlight an object can absorb and how much ice can turn into gas as it warms. With limited surface exposure, energy input should also be limited and activity should remain modest and uneven. 3I Atlas breaks that expectation completely. Despite its compact size, it produces a dense coma, strong jets, and a visible structure that rivals or exceeds comets many times larger. This creates a physical imbalance that cannot be ignored. The amount of gas and dust leaving the object suggests a mass loss rate that should weaken its structure rapidly, especially during periods of increased solar heating. A loosely bound nucleus under that stress would normally fracture, spin erratically, or shed large chunks of material. None of those signs have appeared. Instead, 3I Atlas remains coherent, maintaining its overall shape while continuing to expel material in a controlled way. That persistence forces scientists to rethink where the energy is coming from and how it is being managed. One possibility is that the object has an unusually strong internal composition, allowing it to resist forces that would destroy a more fragile comet. Another idea is that activity is not spread evenly across the surface, but focused through specific regions that release pressure without destabilizing the whole body. This kind of behavior would require internal structure rather than random cracks, suggesting a level of organization beneath the surface. There is also the issue of timing. Interstellar objects are exposed to cosmic radiation for millions of years, which usually creates a hardened outer layer that suppresses volatile activity. 3I Atlas does not appear suppressed. Its activity began far from the Sun and intensified as it approached, without signs of exhaustion or collapse. That freshness raises uncomfortable questions about its past. If it is natural, it may represent a class of interstellar objects that formed under conditions very different from anything in our solar system. If it is not, then the efficiency of its energy use becomes even harder to dismiss. At this stage, scientists are not debating belief, but mechanics. How does such a small object manage sustained output without self-destruction? What internal system allows it to remain stable while losing mass? Answering those questions requires looking beyond size and motion and directly at the properties of the material being released into space. That investigation leads straight to the strange dust surrounding the nucleus and the veil it appears to form. As attention shifted from size and motion, scientists began to focus on the dust released by 3I Atlas because its behavior carried clues that light alone could not explain. Dust may sound insignificant, but in space it controls how an object reflects heat, scatters light, and even hides its own surface. When astronomers measured the particles surrounding 3I Atlas, they noticed something unusually specific about their size. Most of the grains clustered around 10 microns, which is roughly 1/10 the width of a human hair. That scale matters more than it seems, because particles smaller than this are easily pushed away by sunlight. Radiation pressure from the Sun acts like a steady wind, sweeping fine dust outward almost instantly. Larger grains behave very differently, since their mass allows them to resist that pressure and stay close to the source. 10 microns sits in a narrow middle range. These grains are heavy enough to avoid being blown away, yet light enough to be lifted by escaping gas. That balance makes them ideal for forming dense clouds near the nucleus. This is where the idea of a veil begins. When scientists calculated how thick this dust cloud was, they found something unsettling. The density was just high enough to block a direct view of the core while still allowing scattered light to escape. In physics, this balance is described using optical depth. An optical depth close to 1 means the cloud is neither transparent nor fully opaque. It hides details without revealing emptiness. For a natural process, landing precisely at that balance is rare. Dust clouds usually thin out quickly or become so thick that light struggles to pass through. The veil around 3I Atlas sits in between, almost as if it were tuned. This has major consequences for observation. Telescopes may be seeing a blurred shell rather than the true surface of the object. Brightness estimates become unreliable because scattered light exaggerates size and shape. What looks like a large glowing body could be a much smaller core wrapped in dust. This helps explain why early measurements overestimated its dimensions. However, it also deepens the mystery. Maintaining such a veil requires a steady supply of particles at the right size. Too much dust and the system chokes itself. Too little and the cover disappears. 3I Atlas appears to manage this balance over time. Some scientists argue this could happen naturally through feedback, where increased activity thickens the veil and limits heating. Others point out how unlikely it is for that feedback to remain stable without fine control. The dust also shapes the strange structures seen earlier. Its mass allows jets to carve defined paths rather than dissolving into haze. This turns motion into form, preserving layers and edges that should otherwise blur away. At this point, the veil stops being a side detail and becomes central to the story. It hides the nucleus, reshapes light, and stabilizes visible structures. Understanding why it exists means understanding how material is being released and directed. That realization pushes the investigation toward forces beyond simple heating and toward how motion itself is being altered. The discussion changes once scientists stop treating 3I Atlas as an object moved only by gravity and begin examining forces that come from within. Non-gravitational acceleration is a simple idea because it means motion caused by internal activity rather than the pull of planets or the sun. In comets, this usually happens when gas escapes unevenly and acts like a weak thruster. Those pushes are normally small, messy, and hard to predict because natural vents open and close without coordination. With 3I Atlas, the deviations are clearer and more persistent. Tracking data shows its path drifting away from earlier predictions, even after accounting for known gravitational effects. The likely cause is the jet activity, but the way that activity behaves is what raises concern. Instead of spraying randomly, the jets appear to shift direction in ways that create measurable changes in speed and heading. This gives the impression of a force that is not only present, but guided. NASA has approached this cautiously, emphasizing uncertainties and the limits of current models. Independent observers, however, continue to track brightness and motion closely, reporting changes that occur faster than expected. The gap between those perspectives has fueled debate rather than clarity. At the center of that debate is a boundary scientists rarely like to approach. When acceleration shows direction, rhythm, and persistence, it stops looking like simple leakage. Some researchers, including Avi Loeb, argue that such patterns deserve broader consideration. Loeb does not claim that 3I Atlas is alien technology, but he stresses that dismissing the idea too early can blind science to rare possibilities. If an object were artificial, controlled thrust would explain both its motion and its stability. If it is natural, then physics must account for a level of organization never observed before. Either way, the data forces attention forward rather than comfort backward. And as this object continues its journey, the question is no longer only what it is, but how the scientific world chooses to respond. As 3I Atlas continues to move away from the inner solar system, the focus has shifted from speculation toward preparation and capability. This object has become a stress test for modern astronomy, not because it threatens Earth, but because it exposes how limited our tools still are when something refuses to behave as expected. For space agencies around the world, 3I Atlas is no longer just a target of curiosity, but a signal that interstellar visitors may arrive more often and with greater complexity than anticipated. NASA has responded by strengthening systems designed to catch anomalies early, combining space-based telescopes with large ground networks to track motion, brightness, and structural change in near real time. One major investment has been in data processing, where machine learning models are trained to flag non-gravitational acceleration and subtle trajectory shifts that older methods often missed. Rather than waiting for dramatic events, these systems look for patterns that emerge quietly over days or even hours. The Hubble Space Telescope remains critical in this effort because it can resolve fine structural details such as jets, dust layers, and antitails as they evolve. At the same time, the James Webb Space Telescope adds a different layer of understanding by analyzing chemical composition, revealing which gases drive activity far from the Sun. Together, these tools allow scientists to connect structure, motion, and chemistry into a single picture. Across the Atlantic, European teams are pushing high-resolution spectroscopy to its limits. using both orbital instruments and observatories in Chile to study dust size, gas ratios, and energy output. Their goal is to determine whether the activity of 3I Atlas can be explained by extreme but natural conditions, or whether it points to a new class of interstellar objects. In Asia, agencies bring different strengths to the race. Japan applies experience from asteroid sample missions, focusing on surface behavior and how material escapes without destabilizing the core. China has expanded its optical and radio telescope networks, allowing continuous monitoring that reduces gaps in observation and improves trajectory modeling. India contributes advanced orbital analysis tools, comparing 3I Atlas with earlier interstellar visitors to identify shared features or unique traits. This global effort reflects a shift in mindset. Rather than working in isolation, agencies increasingly share data and cross-check results because no single instrument can answer every question. The emphasis is also changing from confirmation to readiness. Scientists know that 3I Atlas will fade from view, but they also know it will not be the last. Each unusual behavior recorded now becomes a reference point for the future. The lesson is not about belief or fear. It is about recognizing that nature or something beyond it may operate outside familiar boundaries. By investing in detection, coordination, and open analysis, science prepares itself not for one mystery, but for many. And as the next interstellar object enters our sky, the response will depend on what we learned when 3I Atlas passed through and refused to be simple. 3I Atlas arrived as a faint interstellar visitor, but it leaves behind a trail of questions that refuse to fade. New Hubble images revealed a jet aimed toward the sun, a behavior that challenges how comets are supposed to work. Stacked observations exposed a repeating wheel-like structure, stable and layered, unlike anything normally produced by escaping dust and gas. Tracking data showed signs of non-gravitational acceleration, suggesting forces that act with direction rather than chance. Each discovery alone would be unusual. Together they form a pattern that forces scientists to slow down and reconsider their assumptions. This is not a story about proving one theory right or wrong. It is about recognizing that our models still have limits. 3I Atlas may be a rare natural object, or it may represent something we have not learned to classify yet. What matters is that the data is real, the anomalies persist, and the questions remain open. As this object continues its journey into the dark, science is left with a challenge rather than an answer. Because the next interstellar visitor may arrive sooner than expected, and when it does, what we learned from 3I Atlas will shape how we see it.